Two towers, a sword shape, built on a sea that didn't even exist. This hole in the ground will hold a 211-meter tower. Every engineer said impossible. 4 years, 2,067 piles, 8 core walls, one insane engineering decision: watch. This whole story starts with an empty sea and the biggest urban gamble in history. Qatar literally vacuumed the seabed and stacked it into dry land, 38 square kilometers. The entire tower shape came from this, a pair of swords on a coin, literally. Here's the crazy part. Kling Consult designed a tower where no two floor plates are identical.
8 concrete core walls carry the entire 211-meter structure. Each zone behaves differently under load.
This load path is everything. Get one connection wrong and the whole system fails under gravity. Now you might be thinking, why did it halt? Because the engineering challenge was truly massive. Before a single pile goes in, they must know exactly what the ground is made of below. The top 20 meters, loose reclaimed sand and soft marine clay. It can't hold anything alone.
Feel this. Loose sand up top, soft clay in the middle. This hard rock is the only thing saving the project.
The SPT blow counts near the surface were dangerously low. This soil had almost zero bearing capacity. But there was one massive problem. This reclaimed ground cannot support any skyscraper load at all. So they designed 2,067 bored piles straight through the bad soil into solid rock. Every single one. Each bored pile is a meter wide. That's the diameter of a large barrel, drilled 35 meters deep. Without bentonite slurry, the borehole walls collapse. This liquid is the invisible engineering hero here. That rebar cage goes inside each pile. It's 35 meters of steel, taller than a 10-story building. Watch closely. That cage fits with centimeters to spare inside the 1,000-millimeter hole. Precision matters.
Concrete goes in from the bottom up, using a tremie pipe. Otherwise, segregation destroys the pile completely.
Concrete poured from the bottom up. Any air pocket in a pile that depth means complete structural failure. Every single pile gets a sonic integrity test. If the wave breaks, the pile gets rejected and re-drilled. They load-tested representative piles to 1.5 times the design load. The pile barely moved. Good. 2,067 pile tops across a 48,000 square meter plot. The total piling length was 50,000 meters. Here's the crazy part. After drilling, you cut off the top meter, contaminated concrete from slurry. Those exposed bars sticking up will lock into the pile cap above. The skeleton is connecting upward.
50,000 meters of bored pile beneath my feet. More foundation steel than most bridges ever use.
Now you might be thinking, how do you hold back the gulf while digging 10 meters down? The secant piles interlock like teeth. Hard concrete alternating with soft, cut through each other. Where loads were higher, a 1.5 meter thick diaphragm wall reinforced the perimeter. Depth, 10 meters. This single leak could destabilize the whole excavation face. One crack multiplies under Gulf water pressure. They injected expanding grout directly into the leak. The foam expands and seals against Gulf groundwater. Wait until you hear this. The dewatering pumps ran non-stop for over 12 months straight during excavation. 10 meters of excavation in 48,000 square meters. That's a volume bigger than 20 Olympic swimming pools. They measured wall movement every day. Even 20 millimeters of deflection would trigger an emergency stop.
10 meters below the surface of land that was under the sea 5 years ago. Think about that.
The pile cap collects load from the column above and spreads it across multiple piles below. Essential. Blinding concrete first. It sounds small, but without it, the reinforcement sits in contaminated mud. Ground beams tie all the pile caps together. Without them, the piles could splay apart under load. Vibrating fresh concrete is not optional. Miss a void in a pile cap and it cracks under the tower above. In 45-degree Qatar heat, concrete cures too fast. Cracking starts within hours if you don't protect it.
These starter bars will become the column above. The load path from penthouse to bedrock goes right here.
2 full basements below ground, 3 levels of parking and all the mechanical plant rooms. That waterproof membrane is the basement's only protection from the Gulf's groundwater forever. One mistake counts.
This 400mm slab resists upward groundwater pressure from the Gulf. Without it, the basement floods permanently.
The basement slab rebar is 2 complete mats of steel, top and bottom, bound by hundreds of links. 16-hour non-stop pour. If the concrete joint's in the wrong place, it creates a cold joint. Structural defect. Power floating the slab traps the surface cream and creates a finish hard enough for forklift traffic. This single area carries more load per square meter than almost anywhere else in the structure. A design crisis. They thickened the slab by 400 more millimeters and doubled the rebar density. Problem absorbed by engineering. Those columns carry every ton of the 36 floors above. Their concrete strength is 60 megapascals. Every sleeve in that slab was designed 2 years ago. Miss one, and you're core drilling through structural concrete.
Down here is where the invisible engineering lives. Nobody sees basements, but they carry everything.
This is the datum. Every single floor level in 36 stories is measured from this one flat surface. The podium ground floor is 6.1 meters high, nearly double a standard story. It carries the ballroom above. 4.8 meter deep beams. That beam is taller than most apartment ceilings. It carries the tower above it. Those 40mm bars are the biggest standard rebar diameter, bundled in pairs because one bar wasn't enough. Here's the crazy part. C60 concrete generates so much heat curing it can crack itself from the inside. The concrete core hits 71 degrees, 1 degree over the limit. The whole beam could have cracked internally. They pumped chilled water through pipes laid on the beam surface. Temperature dropped back below 70 degrees. That void below is the Qatar Hall, 22 meters high when complete. Every column around it had to be precise. Every floor slab hides a complete network of conduits and starter bars, placed once, buried in concrete forever.
This forest of steel props carries the entire tower above, while the transfer beams gain strength below.
Watch closely what they do next. They remove the props one by one while measuring the beam bending. Now the podium is solid. 8 core wall locations are set. The towers can finally start climbing. 8 reinforced concrete cores. They are the spine. Everything else, floors, facade, MEP, hangs off them. The SKE-50 climbs by itself. Hydraulic rams push the entire platform up, using the wall as a track. Inside that climbing box, workers place thousands of bars every cycle. No crane pick, no open exposure. Walls 3 and 4 use the crane-lifted 150F system. Every new position requires a crane pick. Slower, but precise. 4.45 meters in 2 hours. 1 floor cycle completed. The cores are climbing faster than expected.
Because the tower curves, the formwork face changes angle every floor. These wedge panels compensate for the lean.
Each core wall pour has a strict sequence. Pour too fast, and the formwork blows out under hydrostatic pressure. This is where it gets interesting. As the wall gets taller, the concrete pressure at the form base keeps rising. Solution: slow the pour rate down. 0.5 meter per hour instead of 1. It doubles the pour time though. All 8 cores climbing together. 4 automatic, 4 crane lifted. Each one is a different height. Controlled chaos. Floor 18 and the cores start to lean. The curvature the architects drew on paper is now real in concrete. Before every single pour, they survey the wall position. The staircase inside the core is the only way up. It gets built floor by floor as the core climbs above it. Look at that curvature from the side. You can finally see the sword shape forming in real concrete.
This wall is not vertical. It leans outward more with every floor poured. That's engineered. That's intentional.
Night pours keep the schedule. Qatar's 45-degree days slow curing. Night concrete sets properly and quickly. Floor 30. 6 floors left on the cores. The shape is unmistakable now. You can see 2 swords in the sky. While the cores climb above, the floor slabs chase them from below. 2 construction fronts, 1 building. Each Dockerflex table unfolds like a piece of furniture, but it supports 400 kilograms per square meter of wet concrete. This single problem almost wrecked the formwork schedule. Every floor is a different shape. 36 unique plans. Doka manufactured 10,000 square meters of custom tables. 1 set for each floor. No 2 identical. The TLS raises the table 2 floors in 1 move without a crane. It doubled the speed of the slab program. Every balcony on this building cantilevers further out than the one below. The curve does that to every floor. Every pipe, cable and duct passing through this slab was designed 2 years ago, positioned before concrete.
There's no wall here yet, just rebar and concrete 40 meters above the podium. The view from here is terrifying.
90 cubic meters per hour. That pump pushes the weight of a double-decker bus in concrete every 10 minutes. Floor flatness is critical. A warped floor means partitions don't fit, doors won't close, tiles crack. Unacceptable. Thermal drone checking a 1,200 square meter freshly poured slab for hotspots. Every pour, every floor. The long-span ballroom floor uses post-tensioning. Steel tendons threaded through the slab and pulled tight after pour. 186 kilonewtons per tendon. That's 19 tons of compression locked into the slab to stop it sagging. Floor by floor, the wings fill in. Watch the crescent shape emerge as each slab extends the tower plan outward. Every floor beam is a different curve radius. They're CNC cut in a factory to match the BIM model exactly. 12 tons swinging in the wind 50 meters up. The ironworkers catch it with nothing but muscle and a spud bar.
At this connection, the curved steel beam and the RC column become one structural system.
Shear studs make the steel beam and concrete slab work as one composite section. Double the bending strength. Here's the crazy part. Construction gets faster as you go higher. The system is now fully optimized.
The tower leans, so the column isn't loaded centrally. An embedded steel core resists the bending that creates.
Floor 36, core wall pour, the very last lift of concrete on the structural spine. The cores have topped out. That roof slab is 246 meters above the original bedrock. Vertical distance from the bottom pile to the rooftop. 18 hours of pouring concrete on the roof of a 211-meter tower. In the dark, over the Persian Gulf.
211 meters above the Gulf, the cores topped out. But the engineering challenge is far from finished below us.
The final survey confirms every core wall is within 8 millimeters of its theoretical position over 211 meters. Extraordinary. None of the 5,000 facade panels are the same size. Every single one was engineered and manufactured individually. 650 degrees Celsius bends glass into a curve. Each panel matches one specific position on the tower facade. The laminate holds shattered glass together under impact. Sentry glass, 5 times stronger than standard laminate. Even the aluminium framing is curved. CNC bent to match each floor level's unique arc radius. No straight profiles. This single logistical error cost 4 hours and 1 crane shift. On a project with a 2022 World Cup deadline. GPS tagging every panel from the factory. The crane operator sees the exact floor and position before lifting. Each panel clicks onto a bracket already cast into the slab edge. The connection allows thermal movement and seismic drift. Unitized curtain wall. The whole panel arrives complete. No on-site glazing, just click, seal, and move up. Every single facade bay gets a water test before it's accepted. One leaking joint in 36 floors, found and fixed. The last facade panels are going on the top 3 floors. The towers are almost fully sealed now. The netting drops, and for the first time the whole building is visible without a single obstruction. Stunning. 4 centrifugal chillers for a building this size. Combined cooling capacity, 8,000 refrigeration tons. 16 bar pressure test. 1 hour. Any drop means a hidden leak somewhere inside the riser shaft wall. Every duct turn loses air pressure. The duct layout was computer optimized to minimize every single bend. CO2 sensors in the ballroom ceiling respond to occupancy. More guests, more ventilation. Automatic, continuous. 33,000 volts flowing into the building for the first time. Every engineer holds their breath at that moment. 36 floors of sprinkler testing. Every head, every alarm. You don't get a second chance to test a fire system. The last commissioning certificate signed. Every system in a 211-meter hotel, tested, certified, and ready.
Bringing these history-defining moments to life takes everything we have, and many sleepless nights. Help us by hitting subscribe to join us on our next destination.